Hello everyone. So today we've got BPC students as well, so we can continue with the syllabus. And again, some problems with that class. All right. Okay. So there is one concept. I mean, there is a mathematical relation between force and potential energy. We talked of potential energy, right? So energy, due to the virtue of is its position or configuration of the system. All right. Now, force. Let's say U is given as U of X. Force is given by minus du by dx. For instance, u of x for a spring is half kx square, where x is the compression or extension in the spring from the equilibrium position. So F is given by minus du dx, which is equal to minus of half k dx square by dx. What is derivative of x square?
2x.
Right, 2x. 2 and 2 get cancelled, I'll get minus kx. Force due to spring is minus kx, that we know already. Right? So given a potential energy function, I can get force function. Okay. Now, given any kind of potential energy function, we can get a force function. But this is a one-dimensional case. In three-dimensional cases or two-dimensional cases, what we write is of course, I cap. Potential energy is a scalar function, but force is a vector function. In three-dimensional cases, we write it as F is equal to partial derivative of u with respect to x minus partial derivative of u with respect to y, j cap, minus partial derivative of u with respect to z, k cap. This is can also be written as minus d dx I cap minus d dy j cap minus d dz k cap operating on u, which is a function of x, y, and z. This operation or this operator you talked about in usually in math classes we talk about this as an operator which is written as minus del u. So f is given as minus del u in most general case, where del is this operator minus d dx I cap minus d dy j cap minus d dz k cap operating on u. We'll see an example, then things will become clear. What do you mean by partial derivative of x of a function with respect to x is when you differentiate with respect to x, you treat y and z as constants. For example, if I've got a function u of x comma y is equal to xy plus y, then partial derivative of u with respect to x is I treat y as a constant. So constant into x is constant itself plus derivative of constant is 0. So partial derivative of u with respect to x is y. Partial derivative of u with respect to y, I treat x as constant. So what will I get? If I differentiate this partially with respect to y, I'll get x plus 1. Is it clear? It is little different from, it's the same as differentiation, but the difference is you treat the other variables except variable with respect to which you are differentiating. The other variables you treat them as constants. All right, is it clear? Is this clear? F is given as minus del u. It's called del operator or nabla operator. All right, it's called del or nabla. Nabla or del. I can read this as F is equal to minus del u. Okay. If you want me to repeat anything, please let me know. Now, let's say u is given as x square y plus zx plus y square. So du dx is given by, how do I differentiate this with respect to x, students? I treat other variables as constants. All right. In a separate class, in only dedicated for MPC students, we'll talk about its visualization. But here we don't require that three-dimensional visualization, but we require one-dimensional visualization, definitely. So where we plot a graph and then compare it with the motion. All right. So now what do you have? How do I differentiate this with respect to x? I treat y, z, and y square as constants. So x square into y. What is constant times x square derivative? Derivative of constant times x square.
2xy.
Correct.
Sorry, 2,
Yeah, 2x times y plus
hmm,
derivative of zx is
Z,
z plus
Z.
derivative of y square.
2, 2 y, sir.
No, we are differentiating
Y
with
square.
respect to x. We are
0, sir,
differentiating
0.
0, 0. I treat y as constant, so derivative of y constant is 0. Now let's say I differentiate this with respect to y. How do I differentiate this with respect to I treat x and z as constants. So this is
X,
derivative of x square y is x square plus 0 plus 2y.
2,
How do I differentiate this with respect to z? I treat x and y as constants. So 0
0,
plus x
plus X,
plus
plus
0.
0.
Right, that's it. So now my force would be F is equal to minus del u, or this one. I'll write du dx I cap. So my F is 2xy plus z I cap minus x square plus 2y j cap minus x k cap. This is my force. Net force acting on the particle in this potential energy function is this. And we'll talk about like how does a potential energy function look like. All right, we'll talk about it in a while. So, but this is how you mathematically calculate, evaluate force given a potential energy function. All right, let's say I give you a function. Instead of this function, I give you 2x square plus 3y cube plus 2z. 2x square plus 2y cube plus 3z. Sorry, 3y cube. So how do I differentiate this with respect to x? I treat y and z as constants. So this is nothing but 4x. Derivative of this with respect to y would be
0, sir, 0.
no total function with respect to y. This is plus 0. That's fine. Right. I'm talking about derivative with respect to y. Differentiate this u with respect to y.
0 plus 9y square
9y plus
9y
plus
square
0.
plus 0. Differentiate this with respect to z. 0 plus
0 plus
0
0,
plus
0 plus
3.
3.
3. Now, if I ask you what is the force, net force, how will I write the net force now? Minus du by dx I cap,
Minus 4x I cap,
right?
minus 9y square j cap
Correct.
minus 3k cap.
Correct. If I ask you what is the force at a point 1, comma 2, comma 3, at a point 1, comma 2, comma 3, all I have to do is substitute these values here. 1 is minus 4 I cap, y is equal to 2, so 9 4 36,
Minus
36 K,
8.
minus 3 K cap. That's the force acting on the particle in this potential energy function region at a point 1, 2, 3, 1, comma 2, comma 3. All right. Now let's take another function which is given by a by r power 12 minus b by r power 6. The potential energy function for a force between two atoms is in a diatomic molecule can be expressed approximately as a by r power 12 minus b by r power 6. I need to find the force. F is equal to minus du dr. All right, which is nothing but how do I differentiate this function? Let me know. What is derivative of 1 by r power 12?
Minus 12 into r
Correct.
minus 30.
Correct. So that becomes 12a by r power 13 because there's a negative sign already here. Now this becomes minus 6b by r power 7. Is it okay?
Yes. Yes.
Now this is the force between the two atoms. Usually the atomic molecule has got this force function. All right. Now let's see what you mean by stable equilibrium position. I told you, right? Once okay, let's find out the equilibrium position first. Equilibrium position is case when this is equal to 0, force is equal to 0. Then solving for r, I'll get the value of r for which the particle is in, the system is in equilibrium. But the moment I say equilibrium, the next question should be equilibrium stable, unstable, or neutral. So for that to be stable equilibrium, my f, sorry, my second derivative of u should be greater than 0. All right, that's the condition for C. Remember these conditions as mathematical procedures to find out force, equilibrium position, stable equilibrium position. All right. Its significance, its application, we'll look into that in a while. This is for stable equilibrium position. d2u by dr square is less than 0 for unstable equilibrium position. d2u by dr square equal to 0, neutral equilibrium. All right. Now let's talk about the one-dimensional case where we will find out where we'll see the significance of second derivative being a stable, second derivative being less than 0 unstable, second derivative being in 0 neutral. All right. So let's look into the one-dimensional case now. Let's say I plot string energy, string potential energy function, which is parabolic. U X is a one-dimensional case. Its force function is given by minus kx this way. How do I get this from this? Minus du dx. Minus du by dx is, let's say I've got a slope here is positive. My force is negative of the slope. Du by dx is slope. Force is negative of the slope. If the force is positive, slope is positive, force is negative. Slope is zero, force is zero. It's equilibrium position. Slope is negative, force is positive. So how do I determine the equilibrium positions? Looking at the UX graph, I determine the maxima or minima positions. The position of minima or maxima will tell me whether the particle will be in equilibrium or not at that position. I mean, these are the positions where the particle is in equilibrium. So, this is my potential energy function. Here is one equilibrium position. Here is another equilibrium position. But I told you, look at the curvature over here. Curvature is positive. So for it, and my force function would be this way here, as a function of minus kx here, and force function over here would be this way. For instance, all right, yeah, we'll come to that. Yeah. So now, uh, if I leave a particle on this, let's say there is a track of this shape. All right, this is not actually a track. This is a graph of u and x. But let us say there is a track of the shape. All right, there's a frame of the shape, and I leave a small particle on this one. So this will settle down here. If I keep a particle over here exactly on the top of the apex, the vertex, particle will stay there. If I disturb a little, this will go away. If I disturb this a little, it will come back. So this is stable equilibrium position, this is unstable equilibrium position. But if I've got a potential energy function like this, if I have a particle here, if I displace this a little, it stays there. This is a neutral equilibrium position. So looking at the UX graph, I can think of a particle, I leave a particle on this UX graph, thinking that it's the shape of a, it's a solid curve, solid material shape. Where will the ball settle down? That's the equilibrium position. In fact, that's a stable equilibrium position. The ball settles down over there. But if I keep a particle over here, it stays there. It's a stable. It's an equilibrium position. If I disturb this a little, it'll go away. So it's an unstable equilibrium position. It's very simple to look at the UX graph and tell us whether it's stable or unstable. So I'll plot a UX graph now. You let me know whether it's stable or unstable. How many equilibrium positions are there in this graph? One,
Four,
two,
sir.
three, and four. Yeah, exactly, four. Now, if I leave a particle here, it stays there. If I leave a particle here, it stays there. Leave a particle here, it stays there. Leave a particle here, it stays there. But if I disturb the particle, this will come back, right?
Yes, sir.
So this is a stable equilibrium position. Disturb this particle, unstable equilibrium position,
Unstable.
it will go away. This is stable, unstable. If you note one
Unstable.
thing, stable and unstable will always alternate. All right. You will not have two stables at the same time. Between two stables, you will definitely have at least one unstable.
Yes, sir.
All right. So looking at the UX graph, I can tell you whether the point is stable or unstable, whether it's in equilibrium or not. If I leave a particle over here, will it stay there? No, it will slide down. So this is
Yes,
not an
sir.
equilibrium position at all. For it to be an equilibrium position, it has to be either minima or maxima. All right. Any doubt over here?
No, sir.
Okay. So this is a potential energy function, which is given as you don't have to plot a graph from UX graph to Understand it's an equilibrium position or not. From fx graph, how do I make out fx graph intersects the x-axis? Then it's an equilibrium position. F becomes 0. The y coordinate becomes 0 at x-axis, right? But looking at the ux graph, how do I determine the maxima or minima are the equilibrium positions? If it's a minima, it's a stable. If it's a maxima, it's unstable. If it's a flat plateau, then it's a neutral equilibrium. All right. Now the function is given as u naught times exponential of az cos of ax. Now this is my u given as, right? U is a function of x and z. I have to determine the force function for this one, corresponding to this one. So how do I do it? F is equal to minus du dx I cap minus du dy j cap minus du dz k cap. So F is equal to, what is minus du dx? Differentiate this with respect to x. When I differentiate this with respect to x, partially with respect to x, y and z become constant. So this is constant. U naught e power minus az is constant. Derivative of cos is, what is the derivative of this one? How do you differentiate cos ax? Chain rule.
Minus sin ax
And then
into
Minus sin x
a
into ace.
a
into a, right? So minus sin ax into a. So minus and minus become positive. So this is my I cap. Minus derivative of this, differentiate this with partially with respect to y. That is nothing but 0. Because it is independent of y. You have only y and z, x and z here.
yes sir.
Now, how do I differentiate this with respect to z? U naught cos ax into derivative of e power minus az. What is derivative of e power minus az? With respect to z, I'm talking about. Partially with respect to z.
Yes sir.
So is this correct? And it should be k cap.
Yes, sir, it's correct.
All right. Thank you. So now I've got u naught e power minus az to a sine ax plus u naught e power a minus az a cos ax. So I'll have u naught a e power minus az sine ax plus cos ax is my force function. All right. One time, when we have time, I'll plot this in a app. Right? This is a software. I've shown you conic sections before. In the same thing, I'll plot this and show it to you in a PPT. All right, in a session. In one session, I'll show it to you how do I plot this and how does it look like? How does this look like? How does this look like? How will the equilibrium positions look like over here? I told you, right? It's maximum or minimum are equilibrium positions. So we can look at the equilibrium positions from here and understand whether that particle is in equilibrium or not. So if I plot this one, if I sketch this in a 3D surface in a app, in a software, then you'll be better able to appreciate this, understand this. All right. Now let's look at another question. Got function ax square minus bx. I've got a function ax square minus bx. U is equal to a one-dimensional function ax square minus bx. I have to determine the force, which is F is equal to minus du dx, and I have to determine the equilibrium position of the particle. All right. So how do I do it? I first find the force and equate it to 0. I'll get the equilibrium position. So F is equal to, what is the derivative of ax square minus bx?
Yes, sir.
Ah,
2ax minus b.
right. So this is equal to 0 if I equate. X is equal to b by 2a is my equilibrium position. We should be able to also look at this graphically and tell, right? I just not told you if the graph is a cup upward cup, it's a stable equilibrium position. So if I just plot this a greater than 0 and b greater or a greater than 0 if I plot, I'll get a function like this, which is b by a, and midpoint is b by 2a. That's what we got, b by 2a. Equilibrium position is this one. Ball remains over here. And what kind of equilibrium is that? Stable equilibrium position. How do I make out
Yes,
from mathematically? How do I make out if it's stable or not? I differentiate. Determine d to u by dx square. If this is greater than 0, then it's stable. So what is the derivative, second derivative of this one? What is the second derivative of that?
sir, it's 2a, sir.
2s.
2a.
Minus.
Yeah. So no, it's just 2a. See, the second derivative of u is 2a. So
Yes,
2a
sir.
is greater than 0 for a greater than 0. I plotted this for a greater than 0. So 2a is greater than 0. That means for that equilibrium position is definitely a stable equilibrium position. So U is minimum here. For it to be stable equilibrium position, U should be minimum. Potential energy of the configuration should be minimum. Then it's a stable equilibrium position. A system tries to achieve a minimum possible energy of the configuration. All right.
Yes, sir.
Okay. Now let's do one thing. There are some problems based on like more mathematical and more rigorous, but we'll do it in a separate class. Let's move on to another concept, motion in a vertical circle. All right. Motion in a vertical circle. In horizontal circle, you have seen omega, alpha, centripetal acceleration, tangential acceleration, and all. But in vertical circular motion, we apply, see, we are not bothered about acceleration and time, then we go for energy conservation, energy methods. So that's what we're going to do now. A particle is attached to a string, and string is fixed here at point O. A bob is attached to the string, and this is given certain velocity V naught. So this will go like this. If V naught is high, sufficiently high, you might have experienced that this will go in this complete circle, like this. But if V naught is very low, it will just oscillate like this. But for some values of V naught, it may reach this point. From this point, it may just become a projectile. This is what you might have experienced. If you have played with a pendulum or something, with a ball or with a thread, then you would have experienced this. But we'll mathematically derive these situations in next class. But today we are just going to study the basic case, the most basic case of vertical circular motion, where I talk about the centripetal force. Let the speed be u naught. Let the speed over here be v. All right. So when this becomes completely vertical, or at certain instant point p, let the speed be v. Let the initial speed be u naught. Whenever I'm not talking about time or acceleration, it's easier for me to get velocity using energy methods rather than force methods. So I'll go for energy method now. I want to derive velocity at this point. How do I do it? Let this be theta. Let the radius be r. Let this be h. So how much is this? This is r cos theta. How much is h now? This total is r. So what will be the height to which the particle is point p is particle is raised to the level of r minus r cos theta, right? R
Yes, sir.
minus this, which is r cos theta.
R cost.
But what is r cos theta? That's it. R minus h. If I say this is h, so r minus h by r is cos theta. Cos theta, right? Okay.
Yes,
That's
sir.
fine. Let's keep this aside.
Yes,
We're going
sir.
to use this in tension. When you find tension, we're going to use this. But now let's find the velocity v at this point p. What I do, I conserve energy. There's no dissipation of energy. Total energy at this point is equal to total energy at this point. Total energy to mention total potential energy, I need a reference level. So I'll take this reference level to be this level itself. I can take any level as reference level, any horizontal level as reference level under gravity. But I take this level as reference level so that it becomes zero itself. Zero potential energy of the particle at this position becomes zero. All right. So I'm equating it to zero. I'm taking that as reference level data. So my initial potential energy is zero plus initial kinetic energy is half m u naught square is equal to final. What is the final potential energy? Mgh plus final kinetic energy is half m v square. So m gets cancelled out. So v square is equal to u square minus 2gh. Alright. So I get v as a function of h. So if I tell you the height, I can tell you what v is. Right. So if at u naught, sorry. So is it clear?
Yes, sir.
Now let's find the tension of
Yes,
the
sir.
particle. Tension in the string when the particle is at the lowermost position. So tension in the string would be what's tension in the string? I'll draw the FBD of the particle. Tension is upward. Mg is downward. Centripetal acceleration is u square by r upward. So my equation would be T minus mg is equal to m u naught square by r. So T is equal to m into g plus u naught square by r. This is tension at the lowermost position, TL. L, U, and P. So is it clear? Now let's find the tension at the highest position, topmost position over there. I have got FBD to be tension this way, mg this way, centripetal acceleration also this way, which is v square by r. T plus Tu plus mg is equal to mb square by r. So Tu is equal to mg plus mb square by r. Sorry, mb square by r minus mg. You are not saying anything. Are you sleeping? All right, it's mb square by r minus mg. All right, my bad. Okay, but what is V now? V is this much. Substitute this V over here. Substitute and tell me what you get. M times U naught square minus 2GH by R minus mg. I substituted U square minus 2GH over there, where H is equal to R. At the uppermost position, H is equal to 2R. Substitute H is equal to R and tell me what's the final answer. Tell me what's the final answer. Substitute. And where do you think tension is maximum? Tension is maximum at the lowest point because tension is the one which is making a turn. Here, mg is there is a support of mg to make it turn. So tension and speed is also less over here. As the potential energy increases, its kinetic energy decreases. Tension is not doing any work, right? Tension is perpendicular to V. So if tension's component is along the V is 0. So tension is not doing any work. So there is no change in kinetic energy because of tension, because perpendicular to the velocity always. So at lowermost point, potential energy is minimum. Upmost, like topmost point, and potential energy of the particle is maximum. So kinetic energy is minimum. Kinetic energy is maximum at the lowermost point. If kinetic energy is maximum, velocity is maximum. So to make it turn, I need higher T than at the uppermost position. Okay, tell me what's the
Sir,
value
m
of
into
T?
u naught square,
Uh-huh.
m into
Yeah, correct. M into U naught square,
minus 4 gr
right?
by k minus mg.
That's it. That's it. So U naught square minus 4gr by R minus mg. Or I took m common, right? So minus g. Now, if I simplify this further, what do I get? M by R to U naught square minus 5gr. Alright. So this is a tension at the uppermost position. Now look at the students. If I subtract TL minus TU from TL. TL is higher. I subtract TL and TU. What do you get? I get 6 mg, which is constant, which is independent of the initial speed. So if the particle reaches the topmost point, then the difference between tensions is 6 mg always. This is the important point for us to crack problems. Difference between the lower tension between the lowermost point and the uppermost point is 6 mg always, provided it completes the circle. It reaches that point. If it reaches that point, my difference in tension is always 6 mg, irrespective of with what velocity it is projected. Let's say it's projected to u, it's making a circle. It is projected 100 u. Tension over here increases, tension over here also increases, but the difference always remains 6 mg. All right.
Yes, sir.
Okay.
Yes, sir.
Okay. I know this is a little boring, but once you see problems will be very interesting. I mean, derivations are all this derivation is a little boring. I know. So you'll have to bear with me for another 10 minutes. Okay. Now let us see for what value of u naught will it make the complete circle. So it is tension at the uppermost point is m by r into u naught square minus 5gr. This tension at the uppermost point. If it makes a complete circle, that means string is not slacking anywhere here at any point. String is not slacking at any point. That means, and tension minimum is at this point. If tension doesn't become zero here, it never becomes zero anywhere. If at all it has to become zero, it should become zero here first. So it should become zero in the upper region. Tension cannot become zero in the lower region. If at all it becomes zero, it has to become zero in the upper region. If it doesn't become zero in the upper region, the topmost point, it will make a complete circle. So for this to make a complete circle, Tu should be greater than zero. If Tu is greater than zero, tension is greater than zero at every other point because tension is minimum at that point. If that itself is greater than zero, at any other point it's greater than zero. So it makes a complete circle with a string being taut. So my condition would be U is greater than root 5 GR. All right, for it to make a complete circle, my condition for it to be to make a complete circle is root 5 GR. My U naught should be greater than root 5 GR. All right, now let's solve a couple of problems based on this condition. For instance, I have got a track. All right, let's solve two problems. With that, we'll wind up. I've got a spring, a block attached to the spring. There's a track like this. I compress this part, to compress this block a little, because of which there's some potential energy stored in the spring. When it regains this position, when it comes back to this position, it will have attained some kinetic energy, because that potential energy in the spring is being converted to kinetic energy, or in terms of force, being accelerated towards right with force kx. Now, once it gets detached from the spring, it moves with that same speed v naught. Let's say it reaches the maximum speed v naught, it will move with the same speed v naught. I have to determine, so what should be v naught for it to complete this circle? V naught should be equal to at least 5 gr, root of 5 gr. The question now is, what should be the compression in the spring for it to complete this circle? All right, what should be the compression in the spring for it to complete this circle? So for it to complete the circle, let's go it from this direction. And for it to complete the circle, tension should become 0 here, at least in the worst case. If tension becomes 0 here, it never becomes 0 anywhere else. So it will make a complete circle. So that's the condition. For it to make a complete circle, tension at the higher topmost point should be 0 or greater than 0, greater than or equal to 0. If tension is not 0 there, it's 0 somewhere else here, it will not make a complete circle. It will make a projectile from there, that point. Anyways, so this condition is V naught is equal to root 5 gr. So half mv square is equal to 5 mgr by 2. And this should be equal to half k delta x square. Because whatever is compressed, that's being converted to kinetic energy. Initial potential energy plus initial kinetic energy is equal to final kinetic energy plus final potential energy. That V naught should be equal to root 5 gr. I substitute this over here. I'll get delta x is equal to half gets cancelled out. 5 mgr by k under root. So that should be the compression in the spring for it to complete the circle. There is no dissipation of energy here. All right. This is a Neet based question, all right, or mains level question. What should be the compression in the spring for it to complete the circle is its velocity should be equal to root 5 gr. This gives me an idea of kinetic energy. Mass is given. So kinetic energy would be half mv square, which is 5 mgr by 2. What is this kinetic energy? Where is this kinetic energy coming from? From initial potential energy of the spring, which is compressed to an extent of delta x. If that is compressed to an extent of delta x, initial potential energy is being converted to kinetic energy. So the equation becomes initial kinetic plus initial potential is equal to final kinetic plus final potential. Final potential is 0 because my reference for the spring is 0 is natural length position. So kinetic energy plus potential is equal to kinetic energy plus potential. Potential is 0, kinetic energy is 0 here. So half kx delta x square is equal to half mv square. Delta x I get it this way. There is no dissipation of energy here. But now let us say from here to here, from equilibrium position to this position, the length is L naught, and the coefficient of friction is mu. Now, how much should be the compression in the spring? Look at this. Compression should be more than the previous case because some part of energy is being lost here. From here to here, energy is being lost, and after losing that energy, it should have so much of velocity. So, it should have this much of kinetic energy after losing this energy. So, initial potential energy saved in the system should be more than before because there is a loss of energy. I should compensate for that loss. So, how do I do that? Initial potential energy in the spring minus the loss mu mgl, that should be equal to half half m v naught square, where v naught is 5gr, root 5gr. That's my equation. That's it. We are done with the physics of the problem. See, initial energy minus the loss is the remaining kinetic energy. This kinetic energy should be sufficient enough for it to complete the circle. And that sufficiency is, condition for that is V naught is equal to root 5gr. I substitute the V naught is equal to root 5gr here. So I get delta x from here. So delta x would be, I mean, just simplify that, you'll get delta x. All right. Now let's go for another one. Okay. Let's say it doesn't have to complete the circle, but it just has to reach this point. It has to reach this point, the horizontal level. So what do? Velocity becomes zero over there. It reaches here, stops, comes back. Little more compression, little more height. Little more compression, little more height. Further compression, go to this height. The beauty of energy conservation methods are, I don't have to worry about what is happening in between. There's no friction. I don't have to worry about what is happening in between. I can just talk about the initial and final configurations and write the energy conservation equation. So here initial energy is half k delta x square. That's converted to kinetic energy. And that kinetic energy is converted to potential energy again. And that should be equal to mg into r. So my delta x should be equal to 2mg by r by k under root. You understand this point?
Yes,
Let
sir.
us say if I just ask you what should be the compression for it to move to an angle of 60 degrees. What do? I find the height over here. This height would be r by 2, because r minus r cos 60, r minus r by 2 is r by 2. So this would be again r by 2. That's it. That's your answer. All right, these are all mains level questions. It's said mains and Neet level questions. Advanced level questions, we'll do it separately in separate class, or where only MPC students are present. But here we have got Likita as well, BPC student, right? Likita, this is very important for Neet. Important in a sense, these models are important. I mean, you have just models. If you just cover all the models, you are done for the exam. But these models are important. These are mains and Neet level questions. All right. If you have got any doubt here, we'll continue. If you don't have if you have no doubt, we'll end the session here. I'll give you a problem as homework. I've got track like this. I leave a particle from here, height h naught. Radius of this is r. What should be h for it to complete the circle? All right. Think about it. We'll solve this in the next class. All you have to do is the velocity over here should be root 5gr at least. So velocity should be greater than or equal to root 5gr. So conserve energy from here to here. Whatever the potential energy is here, that should be converted to kinetic energy with this as velocity over there. So I know the kinetic energy over there. So I'll get the condition for h for which it should complete the circle. That is one case. Next case, when it has friction mu, coefficient of friction is mu, then what should be the height? Now again, height should be more because there is loss of energy. Whatever height you get here, that next height should be greater than this height, because there is loss of energy in the journey, and the resulting kinetic energy will be lesser than before. If at all, I leave it from the same height. All right. Okay, students, will stop here. Thank you all. You are going to have a class in the evening at 6:30. So do join. Any doubts over here? Ashita? All right, then bye everyone. Have a nice day.